we are dealing with a dynamic programming technique, and dynamic programming problem can also be named as the multi-stage decision making process or the recursive optimization process. The whole dynamic programming problem, the basic philosophy behind is that any complex problem, complex optimization problem can be where the number of decision variables are very high. Not only that, we need to take the decisions at different level, different stages. We decompose the whole problem into several parts and which are being solved sequentially, and starting from one stage we will move to the other stage and we will move further, and these are all interrelated optimization, individual optimization problems, and those are solved with the optimization technique. That is why with the diagram we can just explain in this way. As I explained, the dynamic programming technique could be the forward recursive optimization technique we can adopt, or we can adopt the backward recursive process. If we just discuss the forward recursive process, that means I am in stage n minus 1. Okay. Now, here the inputs are the, for every stage, as we know there are several states. That is why if I consider the n minus 1th state and the corresponding decision is d n minus 1, then the state transformation equation is there, which is the function of s n minus 1 and d n minus 1, and from this stage, if the state is n minus 1, there are several stages, and then we can have the immediate return, that is r n minus 1 d n minus 1. Actually, in dynamic programming technique, this is the essential feature of dynamic programming technique, that we are dividing into different stages. Now, for every stage there are number of state variables, and state variables are responsible to explain the stage, the corresponding stage completely, and state means for every state there is a list of decisions, a decision is there, and we will incorporate the state as well as the corresponding decision, and the state transformation equation T n minus 1 is responsible to convert this state to the next state n, so that we can move to the next stage n. That is the basic idea of the multi-stage decision making process. Now, whenever we are considering state n minus 1, here we need to calculate, this is an individual optimization problem, that is why we need to calculate the corresponding return, that optimal return I am gaining from this stage f n minus 1 s n minus 1, and this value is important if I am moving to the next stage n, because it is not important for stage n how we have reached to this value, only this value is important. Thus, in stage n as well we have the state transformation equation T n, that is the function of S n and the decision d n, because in stage n there is another possible decisions are there, alright, and the trace transformation equation T n is again converting this state to the next state n plus 1. That is the idea for multi-stage decision making process, and for every stage there are alternative decisions are there. Not only that, for every decision how much return I am gaining, that information we need, and we have to calculate the optimal return from this stage, and this is the, we are following the recursive relation for this, and this recursive relation, as we know, this is equal to f n s n is equal to optimal over S n, and we are considering the immediate return of this and the previous optimal return from the previous stage, that is Fn minus 1, that is important for the forward recursive relation. In other way also we can write it optimum Rn Dn plus Fn minus 1, and this Sn minus 1 we got it from the previous stage, that is why there is a stage transformation equation, that is T S n minus 1 d n minus 1. That is the basic idea for considering the optimal solution of the current state. This is the, we have considered the forward recursive relation. I am calculating the optimal value for the nth stage, which is dependent on the optimal value of the previous stage. That is the principle of optimality, as I explained before. This principle of optimality says that whenever we are in the current state, that is only dependent on the information about the detail about the current state, that how many state variables are there, how many decisions, alternative decision we can take in that stage, and not only that, we need to depend on the information about the optimal solution of the previous stage. We do not know, we do not have to have the information how we have reached to that point. What is the path up to coming up to that point? That is not needed. That is the beauty of the decision dynamic programming problem. Once we are breaking into several parts, we can concentrate on the individual part, and we have to take decision for that part only. Now, here the things we need to understand, we need to discuss that how to decompose the problem into different stages. That is more important for us. This is the first question, first key feature of the essential feature of the dynamic programming problem. Once the stage is being defined, next comes how to define the state variables. That is more important, because for each stage there are a number of states, and the number of states are being mathematically represented with the state variables. That is why this is very important. But how to select the state variables, there is no hard and fast rule. This is from the experience only, we have to formulate the state variables. This is the next. The other thing we need to know, what is the transformation equation? I have already discussed in the last class, transformation equation, and we have to formulate the recursive process. We have to decide whether this is forward recursive process or backward recursive process. Accordingly, we have to formulate the recursive relation. That is the mathematical equation we need to formulate. Now, here one thing is very important. Whenever we are taking the decision, just look at the variable dn. Dn can be discrete, dn can be continuous even. That means dn, there is a domain of dn. If the domain of dn is discrete, how to handle that? How to construct the stages? How to construct the states? These I have already discussed before. Now, coming to the next, when the decision space is continuous in nature, how to handle that kind of problem? That part now I am going to discuss, but with some example I will explain to you, so that it would be clear. Now, once we are taking the decision space as continuous, then we are saying that individual stages are the individual optimization problem. Thus, the class, since it is continuous, classical optimization techniques are very much applicable in individual stages, because the spaces, the functions are continuous in that, and continuously differentiable as well. That is why let me take the simple model first, that is the model 1. Where we are considering the objective function as f2 x2 up to fn xn, where x1, x2, xn, these are the variables involved in the decision process. Now, this is a multivariate optimization problem subject to say and it is also given that xi greater than equal to 0, where I is equal to 1, 2 to n. This is our problem. Now, we can divide the whole problem into n stages because n decision variables are involved, and by looking at the pattern of the model we can divide into n parts, and for individual stage we can define the state variable and we will solve it. Let us see how we can do it. Now, we have taken single additive constraint, and multiplicative separable returns. One thing you have to keep in your mind that if the objective function as well as the constraints are not, we are not able to break it properly, then better not to use the dynamic programming technique, because decomposition is very important. At the time of decomposition, we have to keep in our mind that for every stage we should declare the corresponding state variable. If it is possible, then only apply the dynamic programming technique. Now, let us consider there are n stages, and the first stage when n is equal to n, and the corresponding state variable we can declare as Sn as a x1 plus a2 x2 up to a n xn. Okay. Let us move to the next state, Sn minus 1, and let us consider in this way a1 x1 plus a2 x2 plus a n minus 1 xn minus 1. Then we can write this form as Sn minus a xn a n xn. Alright. That means, if we are in the nth stage, we can reach to the n minus 1th stage with this relation. Thus, this relation is the transformation equation, states transformation equation, and this is dependent on the value of Sn as well as a n xn. Let us move to the next, Sn minus 2. This is equal to a1 x1 plus a2 x2 up to a n minus 2 xn minus 2. Certainly again the state transformation equation is Sn minus 1 a n minus 1 xn minus 1. Similarly, if I just proceed further, we will get S1 is equal to a1 x1, and this is certainly dependent on the previous state, that is S2 minus a2 x2, and this is the state transformation equation. If we consider the state variables like this, and if we consider there are n stages, now we will look at the objective function. Let the objective function optimality we wanted to achieve as a maximization problem. It could be minimization as well, the same process is there. Same process means only the difference would be in the consideration of the objective function, but the state variable or the stages definition you may consider as same as this one. Okay? Then up to this, once again I am just saying that this is the problem of n variables. We are trying to decompose the problem into n stages. For individual stage there are state variables, and Sn is the state variable, and you could see that Sn is moving in the continuous space because xi's are continuous. Xi can be positive, it could take any value, that is why Sn moves in the positive. The whatever alternative decisions we are taking Dn, these are all the continuous and the positive values. Similarly, the state variable in the next state, that is n minus 1, this is also continuous, these are all continuous. Now, we have formed the stages, we have formulated the state variables, we have defined the states transformation equation for individual states. this transformation is responsible to move to the next state, that means it is dependent on the previous state in this way, then we can formulate the recursive formula in this fashion. That means return from the nth state is equal to maximization of f n x n plus f n minus 1 s n minus 1. That is the optimal solution. This is known to us. That is why these are only variable for us, and we can construct very easily starting from f1 s1. f1 s1 is very easy to select because it contains only one variable. f1 s1, once we know it, we will move to f2 s2. That means we are doing the forward recursive process. f2 s2 again would be the maximum of f2 x2 plus f1 s1. In this way we will move to fn sn, and this is the final result. Whatever optimal we are achieving here, that is the optimal solution for the whole problem. That means in each time the optimization occurs in the single variable. How it is coming as a single variable? Let me take one simple numerical example, then it would be clear to you. Corresponding to this model, where we are considering the single additive constraint and multiplicative separable returns, there are 3 decision variables are there, x1, x2 and x3. We wanted to maximize x1, x2, x3 subject to x1 plus x2 plus x3 is equal to 5, and x1, x2, x3, these are all positive values. Now we need to solve it. Dynamic programming technique is very nice technique to solve this problem. By converting this problem into 3 stages, we will start from the first stage considering x1, only the variable x1. Next we will move to the next stage, that is f2 x2. In this way we will proceed. For that thing we need to consider the state variables. Therefore, let us define 3 state variables as S1 is equal to x1, S2 is equal to x1 plus x2, S3 is equal to x1 plus x2 plus x3. These are the variables we are considering, as we did for the previous general model, the same model it is. If this is so, we can write it as, just see, these are the stress transformation equation, S3 minus x3, because x1 plus x2 comes from here, and if I just move to the next, this is equal to S2 minus x2. These stress transformation equations are very important for doing the optimal solution. Now our first optimization problem, f1 s1 is equal to maximization of x1 only. x1 is positive, that is why we can consider x1, and this is related with this relation. Let us come to the next stage, f2 s2. I should consider capital, because in the model we have considered capital F. f2 s2, if we consider, this is equal to max, only x2 is varying, x1 and this is x2, f1 s1, and what is the value of f1 s1? This is the value is x1. Thus, we can write it as S2 minus x2. Now, this is the problem of single variable. Now, we have to maximize over x2, That is why we can apply the differential calculus method. Differential calculus techniques tells us that we have to differentiate this function with respect to x2 once and we will equate to 0 and we will get the corresponding optimal solution, and we will go for the second order derivative. In the second order derivative, whatever not optimal, whatever point we got, stationary point we got, we need to check whether this is maximum or not. For if the second order derivative is coming negative, then it is maximum, if it is positive it can minimum. That is why if we apply the differential calculus technique, we can do it. We will get x2 is equal to s2 by 2. That is very easy to say, because first with respect to x2 it is s2, second is the 2x2 equal to 0. From here we are getting the x2 value as s2 by 2. That is the optimal in the second stage. Now we will move to the next stage, and as we know the principal optimality, it says that if I move to the next stage, that is F3 S3, then the recursive process is that maximization over x3, x3, F2, S2, alright, and F2, S2 just now we got this value, that is why here also we can write down the same, and we will just convert this optimization problem with a single variable. How? Just see. What is F2 x2? F2 x2 was the maximization over x2, this part I am just writing. This is equal to x2 s2 minus x2. Just now we have seen that maximum occurs when x2 is equal to s2 by 2. That is why let us substitute here this value, then we will get maximization over x3, and this is s2 by 2, s2 minus s2 by 2, alright. This is the, now it is the problem of single variable, and it is coming maximization of x3 s2 square by 2, and this is s2 square by 4, that means s2 square by 4 we are getting. And just now we got the relation that s2 is equal to s3 minus x3. We will substitute this fact here. Then we will get maximization what you could see here, that the optimization problem in stage 3, it is converting to the optimization problem of single variable x3 only. And what is your S3? S3 is equal to x1 plus x2 plus x3. This must be is equal to 5, because that is a constraint we are having. That is why we have reached to the final stage, and here this is the problem of single variable. Again the same technique, differential calculus method we will apply here, and we will get the relation here. By applying the differential calculus technique, we will get x3 is equal to that star, that is optimal, equal to s3 by 3. Now just now we have said that S3 means x1 plus x2 plus x3, that the value is equal to 5, because that is a given constraint for us. Thus we can say that this is equal to 5 by 3. Once we have reached to this point, x3 is equal to 5 by 3, we have the relations with us, that is S1 is equal to, I need not to write it again, just let me show you. Just now we have S1 is equal to x1, S2, x2, this relation, and from this relation, by substituting the value of x3 as we got, this is equal to 5 by 3, that is 5 minus 5 by 3, we will get S2. Once we are getting x2, after substitution we will get the value for S1. In this way we can say that the optimal solution is x1 is equal to 5 by 3, x2 is equal to, let me put star here because these are optimal values, 5 by 3, and x3 star is equal to 5 by 3. With the objective function, that is f star, it is equal to this value, because the value is x1, x2 and x3. That is all about the model I wanted to say for the problem of the single additive constraint and multiplicative return, and we have applied the dynamic programming technique. Thus, formally we can say that we can summarize the process, the dynamic programming process as this one. The first step is the define the problem means specify the objective function and the constraint, that is our problem. Then decompose the whole problem into several stages. Once stages are fixed, we need to determine state variables and we have to fix about the decision required at each stage. We will move to the third. We will specify the relation that how one stage can be moved to the other stage, rather one state of one stage can be moved to the other state of the other stage. That is why we need to define the state transformation equations. Once we are forming the state variables, from there we can formulate the state transformation equations. As we did there, because we had the state transformation equation in this case, that S1 is equal to S2 minus x2, S2 is equal to x3 minus x3, etc. These are the state transformation equations, and then we have to decide whether we will adopt the forward recursive relation or the backward recursive process. That is why decide whether to implement forward or backward recursive process. Then we have to reach to the last stage, and after that we have to take the decision about the whole problem. That's it has been said that after reaching to the last end, make a representation about all stages, rather the optimal solutions of every stages, and then take optimal decision. These are the steps. Now, that much just I wanted to convey regarding the continuous. No, I will take some other models as well, but before to that, depending on this model, let me consider one problem here which contains uncertainty as well, but the problem is of similar type. We have the single additive constraint and multiplicative severable returns. This is the problem for us, and here the probability factors are involved in the process. Just look at the problem. A government space project is conducting research on a certain engineering problem. Now, 3 research teams are currently involved for solving the research problem. Now, the estimates are in the present circumstances, actually the estimates regarding their failure of the respective teams are given. If we consider the teams as A, B and C respectively, then we have the chance figure so that the corresponding team will not succeed are 0.4, 0.6 and 0.8 respectively. Once we have this information, that means at the current state, if the organization wanted to involve these 3 teams, the same teams in the project, then there is a probability of failure, that is the multiplication of 3 failures together, and it is coming 0.192. Now, the organization wants to reduce this value. Thus, they wanted to introduce few new scientists in this process, and at the most they can add 2 scientists in 3 teams, and if they want to introduce 3 scientists here, what are the probability for estimates are given here also. It is says that since the objective is to minimize the probability, the decision has been made to assign at most 2 top scientists in all teams in order to lower the probability as much as possible. The following table gives the estimated probability that the respective teams will fail when 0 scientists are being added, that means the current situation 0.4, 0.6, 0.8. If 1 scientist is added to team 1, then the failure will reduce to 0.2. If 1 scientist is added to team B, 0.4 reduced to 0.4, 0.8 is reduced to 0.5. Similarly, if 2 additional scientists are added, then team A, the situation is little better. The probability of failure is coming down 0.15, 0.20, 0.30, but the situation is such that we wanted to reduce the probability of failure, but total number of scientists are 2. Therefore, which scientists to be allocated, additional scientists to be allocated in which team, that is the question for us. Thus, this is the objective of the problem, how should be the additional scientists are allocated to the team so that the failure rate will decrease. That is the whole problem. If we consider this problem, then again this problem can be solved with a dynamic programming technique, and dynamic programming technique will convert the problem into several stages. Here the stages are being considered by considering 1 team at a time. First it has been considered, say, team C, and we will analyze the situation, we will get the optimal decision if we consider team C, then we have moved to team B, then we have moved to team A. In that way the stages are being constructed. Thus, we can say that this is the problem for us, that is minimization of the total probability of failure, that is coming because these are all independent events. That is why the total probability of failure would be multiplication of all events, and P1 x1 is the probability of failure for team 1 if it is assigned x1 number of scientists, x1 can vary from 0, 1, 2. Here P2 is x2 is the probability of failure for team 2 if x2 number of scientists are being allotted, and x2 can again take the value of 0, 1, 2, similarly P3 x3. And there is a constraint that total number of scientists must be 2, that is why x1 plus x2 plus x3 equal to 2, x1, x2, x3 these are all positive values certainly, and there is another constraint that these are all the integer values. That is why this is the integer programming problem, and we can solve it with the dynamic programming technique very easily. Now, you see we have considered the states, Sj are the state variables, Sj are the corresponding decisions. Thus, we can have the recursive equation that j plus 1th decision, optimal decision for j plus 1th state is dependent on the jth state. Okay. Thus, if we start from j is equal to 3, that is if we consider the last team, that is team C as the first stage, because we wanted to move backwardly in the backward recursive process. Therefore, Fj Sj is equal to minimum of P3 x3. Here only one variable is involved, that is x3. These are the decision variables and Sj are the state variables for this. Now, this is the problem for us. Now, this is the first, this is stage 1. Let us stage 1. Let us move to the next stage, that is stage 2, and look at the problem. We are adopting the backward recursive process, that is why j equal to 3 we consider, that was stage 3, that was not stage 1. Now, coming to the next stage, that is second stage, j is equal to 2. These are the state variables 0, 1, 2 and x2 is the decisions we can consider, either it could be 0, it could be 1 and it could be 2. Now, if x2 is equal to 0, that means we are not including any new scientist in second team, but S2 is equal to 0. How S2 is being constructed? S2 is equal to x2 plus x3. That means S3, that is a stress transformation equation, S3 is equal to S2 minus x2. As we did for the continuous case, the same problem occurs here. Then we can calculate the probability value when x2 equal to 0, S2 equal to 0. That means no team is getting, team B or C, they are not getting any new scientist. Then the probability would be the multiplication of the corresponding probability 0.6 and 0.8. For 0 addition, it is coming 0.48. Now, for the next, when x2 is 0 but S2 is 1, that means team C got one scientist but team B did not get any scientist. That is why by considering the probability value, we have to calculate the probability, that is coming 0.6, that is team B is not getting any scientist, but team C is getting one scientist, that is 0.5. But in the next, if we consider team C is getting 2 scientists, team B is not getting any scientists, then the probability would be 0.6 into 0.3. That way we have calculated, just see 0.6 into 0.3. Come to the next, x2 is 1, S2 is 0, not possible, because S2 is equal to x1 plus x2. x2 is 1, S2 is 1, that means team B got 1, team C did not get anything, that is why 0.4 into 0.8, that is equal to 0.32. In this way we have completed the whole. Similarly, for x2 equal to 2, S2 equal to 0, S2 equal to 1, it is not possible, S2 equal to 2 is only possibility, team B is getting 2 scientists, but team 1 is not getting any scientists. That is why up to this, whatever analysis we have done, we have analyzed the situation for team C in the first stage, then team B and C together rather in the next stage, and we can get the corresponding optimal solution. This is the stress transformation equation, F2 S2 is equal to P2 x2. Certainly this would be minimization of P2 x2. And P2 x2 and F3 star S3 star. And in the previous case no alternative was there, that is why we need not to take any decision, but here if we consider the minimum values, that then we are getting these values. Now we are moving to the next stage, that is stage 1. Stage 1 means we are considering the teams A, B and C together, and here the stage transformation equation is S1 is equal to x1 plus x2 plus x3. Just now we have seen x2 plus x3 is equal to S2. That is why this is equal to x1 plus S2. In other way we can say that S2 is equal to x1 minus x1. This is a states transformation equation for us. And here the same logic we are adopting. Team 1 is getting 0 scientist and altogether there is no inclusion, that is why the probability is coming 0.192. That was given previously already, that if no team is getting any new scientist, then this is the probability for failure. Now consider randomly any value, that x1 equal to 2. That means team A is getting 2 scientists, team B and team C, they are not getting anything. That is why the probability is coming from here for 0. S2 equal to 0, the optimal value is 0.48. We have just taken 0.48 and 0.15 is the probability of failure if team A is getting 2 scientists at a time. Therefore, the total probability is coming 0.072. In that way, we have just completed the table. These are the infeasible options for us. If this is so, then we can see for S1 equal to 0, this is the optimal solution. S1 equal to 1, this is the optimal solution, and S1 equal to 2, this is the optimal solution. And from the least, if I pick up the minimum one, because I have the recursive optimization equation F1 S1 is equal to minimization of P1 x1 and F2 x2, then this is the minimum value, 0.06 is the minimum value. And how we got 0.06, that is important for us. Just look back the table. Here we have considered that S1 equal to 2, S1 equal to 2 means, and x1 is equal to 1, that means S2 equal to 1. Here, go here, then S2 is equal to 1, we are getting 0.3, that is why we have just picked up the value, optimal value in this stage. Thus, this is the Bellman's principle for optimality. Whenever you are in the current stage, that is only dependent on the previous state optimal value, it is not dependent on anything else. The whole information about the current stage and the optimal values for the previous stage. That is why from here we are getting 0.06, we are getting x1 star is equal to 1, that is optimal, and we got S1 equal to 1, S1 equal to 2. Okay. How we can get S1 equal to 2, and with this then we can get the value for S2 is equal to 1 as I said, and this S2 equal to 1, how we got 0.3, look back to the previous table. That is why that is the last stage of the dynamic programming technique, is that you have to trace back the whole optimal solutions. So that from here I will come here, I will move 0.3 has been used, come here, 0.3, where is 0.3? 0.3 is here. What is the option? Then only you just get that x2 is equal to 0 and S2 is equal to 1. What is S2? S2 is just now we got from S2, if we know S2 and x2, we will get S3. That means we are getting x3 is equal to 1. That means the conclusion says that add one scientist in team A and one scientist in team C, no inclusion in team B, then the probability value, that is the probability of failure, joint probability of failure will reduce from 0.192 to 0.06, and that is the beauty of dynamic programming technique. Even we have the situation where the variables are moving in the discrete space and the alternatives are dependent on the probability values, but still we can calculate the solution for it. Now, let me discuss the next model, because once you will do different models together, you can have certain idea that how to construct the stages, how to determine the state variables. That is why that experience one need to gather. That is why I am coming to the next model, model 2. Model 2 considers single additive constraint and additively separable return. Thus, the optimization problem can be considered as max z equal to f1 x1 plus f2 x2 plus fn xn subject to a1 x1 plus a2 x2 n xn equal to b, and xi's these are all positive, that is a non-negativity constraints for I equal to 1 to n. If we look at this model can be solved with a classical optimization technique by forming the Lagrange function. This is one way for solving it. Another way is that this objective function is the separable objective function, as well as the constraint is also separable. We can adopt the separable programming technique for solving this, but we can also apply the dynamic programming technique, that is the defining stages, defining state variables, etc., further. That is why let us start working on it. Let us first define, since n variables are there from your experience, you must have realized that we will consider n stages and corresponding n state variables we will consider as this one. Similarly, we will move to S2, that is a1 x1 plus a2 x2, and S1 is equal to a1 x1. If this is so, then we can formulate the state transformation equations very nicely here. What are the state transformation equation? This is equal to, can be written as S2 minus a2 x2. Similarly, this can be written as S3 minus a3 x3. Similarly, this can be written as an xn. These are about the state variables. Once we have constructed this number of stages, corresponding state variables, decisions are moving in the continuous space, because xi's are all moving in the continuous decision space. That is why we have to adopt the classical optimization technique for solving it. And not only that, we have formed the state transformation equation, that means how one state is moving to the other state. Now, the only thing is left, that is the recursive formula. We can use the forward recursive equation, we can use the backward recursive equation as well. Now, recursive formula can be written very nicely again. Fn Sn is equal to, by considering one variable at each stage, then nth stage would be Fn x, I am sorry, this is not Fn xn, this is the objective function Fn xn plus Fn minus 1 Sn minus 1. That means the nth stage is dependent on n minus 1th stage. Thus, we have to move the process from F1 S1, then we will go to F2 S2 by considering max of x2, F2 x2 plus F1 S1. F1 is S1 is the optimal value of the previous state. In this way, if we just proceed, we will move to Fn minus 1 Sn minus 1. This is equal to, if I write again xn minus 1, this is the objective function in the nth stage. And then we will reach to the final stage, that is the whole problem will be addressed once we will calculate this. This calculation will be based on this recursion formula. Now, we can see that for each stage we are solving only one optimization problem at a time, and you have experienced the model 1. In the similar way we will handle it. Let us consider some numerical example so that you can understand this model in a better way. greater than equal to 15, the value is there, alright. There is no equality constraint, single additive constraints are only there, and these are not integers, these can be in the continuous space, it can take any real number x1, x2 and x3. Now, very quickly let me do the problem. Let us consider the first stage variable x1, the second state variable, not stage variable, state variable. Then it is equal to x1 plus x2, that means it is equal to, then okay. The state transformation equations I will do later on, just let me consider the, we wanted to convert in one variable, that is why the values are coming here S2 minus x2, am I right? Yeah. This is x3 minus x3, alright. Now, this is given from the constraint, this is greater than equal to 15. Now, we have constructed the stages, we have constructed the state variables as well as the state transformation equation. Let us move to the problem. Let us solve in each stage individual optimization problem. First problem is F1 S1 maximization over x, minimization problem, minimization of x1 square, alright. In other way we can write minimization of S2 minus x2 whole square, okay. Let us move to the next, that is F2 S2. Let me consider the capital F, because we have considered in this model small f as variable name. If this is so, this is equal to minimization of x2 square plus f1 s1. This is f1 s1 for me, that is why we can consider minimization of x2 square plus s2 minus x2 whole square. Now, once we are getting that, just see, second stage problem is a problem of single variable only, x2. We can apply the optimization technique. Move to the next, f3 x3. There, this would be minimization x3 square f2 s2. That means minimization x3 and f2 s2, again we have to convert it further. That is why let us solve the problem. Let us first solve this problem, then only we can construct the, we will get the optimal solution, then only we can construct this one, otherwise it is not possible for us. That is why our problem is coming here, that minimization of x2 square plus x2 minus s2 whole square. Now, if we apply the differential calculus technique, then by differentiating this objective function with respect to x2, x2 is only the variable for us, then it will be 2x2 minus 2s2 minus x2 equal to 0, and this gives the value x2 is equal to s2 by 2. Once we have done so, then our f2 s2 can be nicely calculated, s2 square by s2 minus x2 whole square. After substitution of this, we will get this value as s2 square divided by 2. Okay. Now, let us go for the next decision process, that is again s2 is equal to, from here we got s2 is equal to x3 minus x3. That is why we can consider this as x3 square plus s2 square by 2. Let me put s2 as x3 minus x3. That is why it is coming again the optimization problem of single variable, alright. That is the beauty of applying the dynamic programming technique. And once we are calculating this, we will get f3 s3 is equal to, and we have reached to the final state, and here the values are given x1 plus x2 plus x3, can be minimum value is 15, maximum value can be anything. Now, our problem is for minimization problem. If we apply the differential calculus technique here, whatever value for x3 we will get, that would be dependent on the value of S3. Therefore, the minimum objective function will be attained when S3 is equal to 15, clear? Thus, we can say that minimum is attaining as x3 square divided by 3, and we need to consider, and here there is a condition that S3 greater than equal to 15, minimum of this, then certainly it would be 15 square divided by 3, that is the optimal value, S3 is equal to 15. Now, once we get S3 is equal to 15, we can calculate S2, we can calculate S1. In other way, we can calculate all the values for x1 star, that is 5, x2 star is equal to 5, and x3 star just now we have calculated is equal to 5, because S3 is 5 plus 5 plus 5, clear? Let me repeat once more this process. S3 will give you the value for S2. Value for S2 means this is the function of x1 and x2, and function of x1 x2 means again we will move to a S1, then we can calculate x1 x2, two equations, two unknowns. From there very nicely we can calculate the value of these. Now, let us move to the next model. Model 3, where we are considering the problem minimization or maximization, anything we can take where the objective function looks like this. These are all in a multiplicative way. Now, here also we can solve it by dynamic programming technique, and we need to declare the state variables. In this way, if we will proceed further, and we will get S1 equal to x1, all right. And from here we can calculate the state transformation equation as well. Thus, I can say that you can apply this for the example minimization of no, this is not the problem. Equal to say 15. And some other problem I can also give to you for practice, that is now that is all about the problem, and this problem solution I can say that xi star would be is equal to that is the solution of this, and that is all about the dynamic programming technique. Thank you very much.